think we're all set.
Thank you, Hannah. Well, let me start off and welcome everybody to this webinar today on September 30th, 2024. We are excited today to have the much anticipated webinar on the topic of MRI, and in particular the advanced MRI whole sequences and our strategy for our advanced imaging that we plan to do in CLARiTI. And just to remind you all, with CLARiTI, this is a project that's providing national infrastructure to the ADRC system. It's intended to complement SCAN and complement the duties and the new responsibilities in the P30 RFA that we all have as ADRCs. And as I looked on the SCAN website just this morning, there's over 2,600 unique individuals with PET imaging from January 1st, 2021 to now. That's 3.5 years worth of PET imaging, and that's really extraordinary. But we know there's about 11,000 or more in our recruitable pool for imaging in the ADRC system. So that means in the past 3.5 years, we've only touched about 25% of the individuals in the ADRC system on whom we could be getting ATN imaging. And with CLARiTI, we want to bring in 2,000 individuals, scan them at a baseline, and then at follow-up, and contribute these images to the ADRC system, have that integrated with NACC, but those images are also part of your local ADRC. And so we'll be touching on some of these things today. We'll be going over the specifics of the MR approach that we plan to have. And as we start this webinar, let's turn the time to Erin Chin, who's the overall administrative lead for CLARiTI, to give us a few updates. So welcome everybody, and we're glad you're here today. Erin, take it away.
Thanks, Sterling. You can head to the next slide, Phoebe. I'll be covering some study updates. Next slide. All right, so let's start off with our CLARiTI box server change. You have a link right there for our new box server. We just thought we would organize it in a little different manner. So we have one box folder that is public for all sites that includes any documents, SOPs, manuals of procedure that sites will need as part of study startup especially. So you can all find it in one place. Next slide, please. All right, so we did have a CLARiTI Connect newsletter that came out last week, Thursday. So if you have not yet read that, please do so. We have a new protocol version 3 and then new consent templates. Those are version 3 as well. So again, an email was sent out to all CLARiTI contacts with this announcement when WCG had submitted the approval to us. So these are now the official study documents. You will have to, even if you've had previously approved version 2 consents, you will need to have version 3 consent templates. And then just a reminder, before you submit to WCG, please send those templates to your CLARiTI project coordinator as well as the CLARiTI regulatory team for review in advance of submitting to WCG. Next slide, please. All right, so if you read the CLARiTI Connect, you'll likely see that we released our CLARiTI study handbook. So there's a lot of great information in there. Take the next couple weeks to peruse our handbook and let us know if you need any additional information, but you can find all sorts of things, what you need to do for site activation, a lot of great information in our case report forms and so forth. So hopefully that is a useful resource for you and your study teams. Next slide, please. All right, and then in that handbook, you can also learn more about the site initiation visits. So I have provided some information on the site initiation visits previously, but just a reminder, we are giving priority on scheduling those to sites that do have WCG IRB approval. And then the site initiation visit will be with our central monitoring service. So that will cover a protocol review led by Sterling, a regulatory review, and then our two project coordinators, Kelsey and Hunja, will be going over the case report forms in great detail as well. And then you'll also hear from the central monitoring service about the monitoring plan that they have for CLARiTI, how often they'll be monitoring your regulatory binder and so forth. Next slide, please. All right, and then a couple of brief announcements. So our last CLARiTI office hours that will be held on October 11th. So we do not have an agenda for office hours. This is just a time where our CLARiTI administrative team, as well as a couple people from the NACC team, will be available to answer any questions that you have. Again, we're not releasing any new information. We don't have an agenda, but feel free to stop in, get your question answered, and you can, hop off whenever you're ready. And then lastly, we're going to have a CLARiTI session at the NACC Fall Conference. So that session is going to be on October 17th at 4 p.m. We'll be closing out the conference. So you'll be hearing from Drs. Johnson, Moramino, and Biber, giving some study updates, talking more about the scientific impact and infrastructure impact of CLARiTI and what that brings to the program. And then we'll be hearing from the Inclusion Core, Dr. Oziomo Okonkwo and Dr. Monica Rivera-Mint. All right, and I think that's my last slide, and I'll pass it off to my partner, Heather at NACC. Thank you.
Hi, everyone. Heather O'Connell here at NACC. At our last webinar, I announced that the Year 1 award will now have a budget period from September 1st, 2024 to August 31st, 2025. An email with details was sent out to site PIs, ADRC administrators, and your grants and finance personnel with more details about that. An important note to reinforce today is that pre-award expenses are allowed up to 90 days. So once your sub-award is processed and executed, any expenses beyond June 3rd, 2024 will be able to be invoiced. Also, we've received sub-award documentation from nearly all the ADRC sites, so thank you for that. And documentation reviews are underway. For budgets and budget justifications, we're checking that the submitted budgets align with the budget and payment terms document that was provided, which is reflected of the funding received and allocated to each of your sites. The letters of intent and seed IRB approvals documentation are also being reviewed to make sure all details are required. This review is prioritized based on the site initiation visit schedule, which is really reflects the site's overall readiness for starting up in the study. So that's how we're prioritizing the sub-awards as well. ADRCs, or after we finish these reviews with each of the sites, we'll be reaching out to each site individually to let you know that the review is complete and if there are any outstanding action items before moving forward. So all sites should be hearing from NACC within the next 2 to 3 weeks if you haven't already. That's the update I have for you related to sub-awards today. Happy to answer any questions in the Q&A down below. And I think that's the last study update, so I'll pass it over to Beth to introduce our guest speakers today.
Thanks, Heather. So it's my pleasure to introduce John Detre. He's a professor of neurology and radiology at the Perelman School of Medicine at Penn. John co-leads the imaging core at the Penn ADRC. He was also one of the initial members of the ADRC imaging core steering committee. And he currently leads the Advanced MRI core in CLARiTI. And he'll be introducing the other members of this team. So thank you, John.
Thank you, Beth. This slide just gives you some pictures and brief descriptions of the Advanced MRI core team supported by CLARiTI. In addition to myself, Dylan Tisdall is a colleague of mine at Penn, who's primarily overseeing with Steve Kecskemeti at Wisconsin the motion-corrected T1 MRI studies. Swati Levendovszky is at University of Washington, and she is overseeing Philips implementations. Konstantinos Arfanakis, who's at both Rush and Illinois Tech, is also part of the team focusing on multi-parametric imaging, and he'll be presenting on the QSM component. Dechang Chu is at Emory, and he's a sequence specialist, and he actually has a research sequence for QSM that will be mentioned. And then Greg Zaharchuk, who I'm not sure is on today, He's a radiology professor at Stanford, and he's an expert in synthetic PET from MRI, which we'll cover briefly in the context of ASL. And finally, Leonardo Rivera is another sequence specialist from University of Washington, Madison, who's overseeing some of the GE implementations with Steve. So next slide. Am I? Oh, you're good. Okay, so the agenda for the next 20 minutes or so is we're going to start with just a brief overview, and then we're going to have some modality-specific presentations on the QSM, the motion-corrected T1, and ASL. And then there'll be a brief review on how we get the protocols and some outlining of the post-processing plans. And as a reminder to everybody, we have a Q&A open where you can type in your questions, and we will have a Q&A session specifically for questions. So if you want to just ask them verbally, that should be possible too. Who's advancing the slides, me or you? I'm confused.
I'm sorry, there was.
Okay. All right, good. So, you know, as Sterling mentioned, the overall goal of CLARiTI is to scan 2,000 people with ATN and with a little bit of V imaging. And, you know, one of the goals is to try and create individual etiologic profiles from imaging in plasma of multi-etiology dementia. And as part of the support for ATN imaging, there's support for a research MRI scan. The very basic minimal requirement for this MRI scan is the scan T1, which is you know, T1 weighted MP range image that's a marker of neurodegeneration. And then FLAIR, which shows white matter hyperintensities that are approximately a measure of vascular injury. And then the remainder of the MRI session is flexible. And in conceiving of this, the idea behind the CLARiTI Advanced MRI initiative is the idea that we could use some of this funded time to test research protocols for neurodegeneration to try to see if we can use some state-of-the-art or even forward-looking kind of bleeding-edge imaging methods, and while doing that, validate CLARiTI as a platform for dissemination and validation of advanced MRIs more generally. And in preliminary surveys before the project was submitted, nearly all sites expressed interest in this, and we're hoping now that CLARiTI is underway that many or all sites will participate in at least components of the advanced MRI. Next slide, please. So here is what the CLARiTI MRI protocol looks like. As I mentioned, all MRI studies must include the scan T1 and the scan FLAIR. These are intended to be acquired first. And then QSM is kind of in the middle of advanced MRI and standard, in the sense that what we are proposing for QSM under advanced MRI is really product sequences. So it should be just as easy to implement as the scan T1 and FLAIR. And Konstantinos will go into a little more detail on what the characteristics of the imaging are. But the goal of the QSM was initially to quantify regional iron deposition as an additional useful biomarker for patterns of neurodegeneration, and additionally to identify microhemorrhage, superficial siderosis as it relates now to to amyloid angiopathy and risks and monitoring of patients on anti-amyloid therapy. So we would really like to see every site perform some sort of QSM, and ideally the specific implementation of QSM that we're recommending under advanced MRI. But if not that, then at least some sort of multi-echo GRE that can be used to look for microhemorrhages and iron deposition. So the advanced MRI, the real advanced MRI, what makes it advanced is that we're using non-product sequences or procedures. And so we're down to 2 of those, although there are additional advanced sequences that we are entertaining for future deployment. And again, as part of the general validation of the CLARiTI platform for advanced imaging, hopefully over time, we will have the opportunity to try additional advanced sequences. But the 2 we picked as being most ready to go out of the gate are motion-corrected T1-weighted MRI. So these are sequences that can assess the impact of patient motion, participant motion, as well as its correction on morphometry metrics. And Dylan will be introducing that in a couple of minutes. And then finally, state-of-the-art ASL MRI, which is a method that I've been involved in my whole career, and creates a non-invasive map of cerebral blood flow or perfusion with the idea that there are ADRD-related patterns of hypoperfusion, and that furthermore, this information can be used in combination with structural MRI to generate an MRI-based synthetic FDG PET. I will also briefly address the idea of a perfusion MRI as a vascular biomarker. So that's option 1. That will take a little bit of extra effort to get some new capabilities onto your scanner. On the other hand, you will have those capabilities to use for other things, should you like them. Option 2 is the so-called full CLARiTI standard protocol, which is really the ADNI-4 protocol. So that's another option. You can just run ADNI. And then option 3 is that you really, apart from the T1-weighted MRI and the FLAIR, and hopefully you'll agree to some sort of multi-echo GRE, can use the time to acquire whatever local sequences of your own choosing. Next slide, please. So now I'd like Konstantinos to take over and just go over some of the concepts and plans around multi-echo GRE.
Thank you, John. So before we look at what we can do with multi-echo GRE, let's see at what we can do with the simple version, the single echo gradient echo. So with simple GRE, we can simply look at the gradient echo images or perform SWI reconstruction and make these cool looking images of venograms. We can detect microbleeds, diagnose hemorrhagic stroke, cortical superficial siderosis, which has been associated with CAA and so on. Microbleeds especially have become particularly important in the era of anti-amyloid treatments and ARIA. So now, what can we do with a gradient echo sequence with multiple echoes? So with multi-echo GRE, we can perform quantitative susceptibility mapping reconstruction and generate susceptibility maps, magnetic susceptibility maps like the ones you see on the left. The reason why magnetic susceptibility, there's multiple reasons why magnetic susceptibility is important. So the first reason, iron has a positive magnetic susceptibility value. So higher iron concentration increases the signal in QSM maps, like what you're seeing here in the basal ganglia, in the substantia nigra, red nucleus, and dentate nucleus. In addition, other work has shown that iron promotes the development of plaques, amyloid plaques, alpha-synuclein aggregates, and tau protein, and also iron increases oxidative damage, leading to neuronal degeneration. So important of iron, important of assessment of iron, the importance of assessment of iron with QSM is quite high. In addition, myelin has negative magnetic susceptibility, and loss of myelin or demyelination is related to higher signals in QSM. So overall, with QSM, we can collect information that you can see clearly is important for ADRD research. At the same time, with multi-echo GRE, we can do everything that we can do with single echo GRE, like detect microbleeds, and actually we can do that better. We can use QSM in order to disentangle true microbleeds and false positives. In the bottom of the slide on the right, you see a gradient echo image and a black hole in the middle of it that is pinpointed by the crosshairs. If you had single echo GRE, you would probably translate that as a microbleed. On the left, you see the same part of the brain, and you see that the magnetic susceptibility is negative, which is the opposite of what you would expect from a microbleed. So this is most likely a false positive and most likely calcification. So with multiple echo GRE, you can do all of the things that I mentioned earlier, plus you can do the things that you can do with single echo GRE and better. Next slide, please. So along these lines, recent work has shown that magnetic susceptibility in the substantia nigra is higher in patients with probable dementia with Lewy bodies compared to cognitively unimpaired individuals. Also, a recent paper review demonstrated that the majority of QSM studies in different diseases, such as Alzheimer's, Parkinson's disease, etc., showed increased magnetic susceptibility in the regions that are known to be involved in these diseases. For example, in Parkinson's disease, there is the majority of papers showed increased magnetic susceptibility in the substantia nigra, in the red nucleus, globus pallidus, etc. In ALS, it was higher susceptibility in the motor cortex, and so on. So these papers again demonstrate the importance of QSM in neurodegenerative diseases. Next slide, please. So how should we run multi-echo GRE on our scanners? One approach, like John mentioned, is to use the scan protocol. We strongly recommend that you use the CLARiTI protocol for multi-echo GRE. The CLARiTI protocol does not involve any new sequences. It involves product sequences, so you don't need to get any new agreements or anything like that. And has a number of advantages over the scan protocol. One advantage is that, and most important probably advantage, is that the CLARiTI protocol collects data in isotropic voxels, 1 by 1 by 1 millimeters, in contrast to the strongly anisotropic voxels of the scan protocol. A second advantage is that the CLARiTI protocol uses sagittal slices, which means that the gradient echo data are in an orientation that is matching that of the NP rays and FLAIR. In contrast, the scan GRE protocol uses axial slices. A third advantage is that the CLARiTI protocol has a wider range of TEs with a maximum TE a little higher than the maximum TE of the scan protocol, which means that the CLARiTI protocol allows better assessment of tissues with higher T2 stars. And the fourth advantage is that the CLARiTI protocol is about 2 to 3 minutes faster, depending on the scanner implementation. So instead of approximately 9 minutes with the scan protocol, with the CLARiTI protocol, it's about 6.5 minutes. So in summary, the multi-echo GRE provides important information for ADRD research. And to run the multi-echo GRE, you have two options. You have the option to use the scan protocol, but we recommend using the CLARiTI protocol. That's all from me.
Okay, great. And now let's have Dylan take over and talk about motion-corrected T1 for a couple of slides. You're still muted for us.
Thank you, John. Sorry. Yep. I just want to quickly introduce the idea of motion-corrected T1 weighted structural scanning and how it's going to be implemented in the Advanced MRI protocol. So the background motivation here is that it's been established at this point across a wide variety of analysis pipelines, morphometric analysis pipelines, that even relatively low levels of head motion tend to bias cortical thickness estimates towards being thinner. And so the figure here on the right is showing the percentage change in cortical thickness per millimeter per minute of subject motion. So 1 millimeter per minute is relatively small subject motion, even for people that are trying to be relatively still. And what you can see is that there's a spatially varying pattern of bias in cortical thickness that occurs as subjects move. Now, this particular figure on the right, was analyzed using the free surfer tools and was generated with healthy controls performing repeated different levels of motion so that we could evaluate this. But in fact, very similar figures with very similar patterns of bias have been generated now with a variety of analysis pipelines and from a variety of cohorts. And so, this seems to be an important effect. On top of which, the degree of motion that we see having these sorts of effects is relatively small, and the effect size is on the order of the effect size often observed in neurodegenerative diseases. And so we feel like this is an effect that it's very important to control. So if you can advance the slide here, then we'll talk about what the sequences are that we're going to try and do this with. So basically what we're proposing here is a suite of motion correction and motion measurement technologies. So the example image here is, this is generated from the GE sequence that we'll be using. On the left is the original motion degraded scan, and on the right is what comes out of the motion correction system applied to the exact same data. So basically what all of these sequences have in common is the ability to both track subject motion or measure subject motion dynamically from the scan data, and then apply a correction. Now on the Siemens and Philips platform, this is going to be implemented via the volumetric navigators system. So this embeds very fast 3D EPI navigators into your normal MP range scan, then uses those navigators to estimate and correct for subject motion in real time. The specific protocol here that will be distributed as part of the Advanced MRI protocol will have its MP range parameters matched to the ADNI4 protocol, but with the insertion of the navigators in addition. So in principle, the scan that comes out should be processable using the standard ADNI4 and scan analysis tools. What you do get out as well, though, as a benefit of this is a second series, which is all the navigators, which gives you a kind of cine view of the subject's motion in the scanner. But more importantly, it also saves the quantitative estimates of the subject motion TR by TR during the scan, which is a very useful regressor for understanding the impact of motion on the subsequent morphometric scores. On the GE platform, we'll be using a slightly different sequence. This is called MP-NRAGE. This is a radial encoded MP RAGE, which instead of prospectively correcting during the scan, is able to retrospectively correct motion, which is why, as you can see in the figure on the right here, we're able to give both the motion degraded and the motion corrected scan from one data set because it's doing the correction retrospectively. This sequence is also very interesting in that it allows both variable T1 weighting to be generated from one scan, and also allows quantitative T1 maps to be generated. And so, critically, also with the MP-NRAGE sequence, similar results to what I showed on the first slide have been demonstrated, showing significant impacts of the motion correction on morphometry, even for relatively minor motion. So, these sequences will, none of these are product sequences at this point. So these will all be custom sequences that need to be installed on your scanner. But for both the GE and Siemens platforms, they're available for a variety of software baselines. And Philips is working to have this available shortly. So that will be the distribution path there. So that is where we are at right now for the motion corrected T1 technologies. Next slide. I think that's the last one. Yes.
All right, so I'm just going to wrap up here with a few slides on arterial spin labeling. So as I mentioned, and most of you probably know, ASL is a approach for non-invasively quantifying regional CBF with MRI. It uses magnetically labeled blood water as a tracer for making CBF maps. And the rationale for using CBF as a biomarker for neurodegeneration is that regional CBF is coupled to regional metabolism. And so patterns of hypoperfusion reflect neural deficits. And on the right, I pasted in a figure from a review article that came out now 10 years ago, showing examples of structural MRI in the middle, and then FDG PET on the left and ASL MRI on the right. And the top panel is normal aging, the middle panel is Alzheimer's disease, and the bottom panel is frontotemporal dementia, illustrating, firstly, that you can detect characteristic patterns of hypoperfusion using ASL MRI, even at the single subject level, if the imaging quality is high enough. And number two, that these patterns closely resemble the patterns that you get using FDG PET. And of course, diagnosis and differential diagnosis of dementia is one of the main clinical uses of FDG PET. And I'll just mention that CLARiTI also includes support for FDG PET as part of the imaging protocol. And we would really encourage sites who have the capability of doing FDG PET to collect that as well. Now, in general, a large number of publications show that there's a pretty good agreement between ASL and FDG PET. However, at the single subject level, the sensitivity and specificity of FDG PET tends to be superior in this application. And that is possibly or even probably attributable to the large variation in quality of ASL methodology, which has really evolved dramatically since it was first reported about 30 years ago. And currently, pseudo-continuous ASL, and this slide should say in parentheses PCASL, not PCAL, with background suppressed 3D readout is the current state of the art. And in fact, this approach has been available on the GE product for over a decade. And the images that I'm showing on the right here are, not accidentally images that were acquired from a site that had a GE scanner. Now, these capabilities have also been available on Siemens and Philips, but as research capabilities. They are becoming product now on new Siemens scanners, but for most of the installed base of CLARiTI, these capabilities are still research. Next slide, please. So just as an aside, these are some preliminary data acquired from our lab in collaboration with the colleagues' lab at Penn, Kate Davis, showing how deep learning methods can be used to bring the diagnostic sensitivity and specificity of ASL or MRI more generally closer to that of FDG PET. And so this is an example of a generalized adversarial network that was trained to synthesize FDG PET from ASL and T1 weighted MRI. And on the bottom panel under then, you can see the quality of the ASL scan that went into this. So it actually shows pretty good sensitivity in gray matter, but the image is very blurry and has poor sensitivity in white matter. It's pretty much black and white matter. And then above it, you can see that colored blob labeled CBF was a representative slice of the ASL scan. And then to the left of it is the T1 weighted MRI. And so this network was trained on a data set that we had available at Penn that was composed of about 80 subjects, about half of whom had mild cognitive impairment, half of whom were cognitively unimpaired older subjects. And the network was trained to generate a synthetic PET combining the high-resolution T1 weighted MRI and the lower resolution CBF map. And then to the right of these arrows, you can see the resulting output from this. And so now, as you can see, the synthetic PET, which is really the deep learning fusion of the T1 and the CBF, now much more closely resembles the original PET. And of course, this is using a network trained on the data that weren't this data itself. So this is truly training. And then all the way on the right, you can see the ROC curves wherein the GAN-derived synthetic FDG PET shows approximately the same area under the ROC curve as the true FDG PET in green, the green line, and both of those are considerably higher than the ASL or the T1. Next slide, please. So what is CLARiTI Advanced MRI ASL? So on the right, you have 8 examples of a mid-sagittal and axial slice from various implementations of ASL over the years. And as I mentioned, the CLARiTI Advanced MRI ASL will use pseudo-continuous ASL with a background suppressed 3D readout. So that's the general technical harmonization across the platforms. On GE and Siemens, except for the newest Siemens scanners that have the product Advanced ASL, it's going to be a stack of spirals readout. And on Philips and those places that have the newest Siemens scanners and also the Siemens Advanced ASL product, it's a GRACE readout. We've selected a 3mm isotropic resolution as the best trade-off between sensitivity, resolution, and scan time. And of course, we hope to be able to use this T1 ASL synthetic PET fusion to further improve the effective resolution of our output CBF maps. Now, our main acquisition will use a single post-labeling delay. So those of you who are ASL aficionados will know that when you do an ASL experiment, you label blood, then you wait for that blood to get into the brain, and then you image it, and you create a CBF map by comparing effectively brain images with and without this labeling. But there's variable delay times from the labeling location to the location in the brain. And some evidence suggests that by using multiple post-labeling delay, you can get a more accurate measurement of CBF. We have elected to focus mainly on the single PLD because the single PLD prioritizes image quality over absolute quantification, because our primary goal is to detect patterns of hypoperfusion associated with different neurodegenerative disorders. And to mitigate the effects of single PLD, we label for a long time and we wait a long time. And as you can see, these bottom 4 methods are the different methods that are available for CLARiTI. And in particular, you can see that not only is the resolution better than the earlier methods, but the sensitivity, at least for the GE and Siemens implementations, you can now see very clear signal in white matter. And in GE, it's fundamentally the product sequence, but there is a research extended ASL sequence that allows us to dial up these particular labeling parameters. Next slide. So let me just briefly mention that although not a primary goal of this project, because ASL CBF is actually a direct measure of blood flow, it should be a good measure of vascular integrity and perhaps more specific to vascular deficits than white matter hyperintensities, which are nonspecific. The most common cause of vascular cognitive impairment is cerebral small vessel disease, which affects arteries that are too small to resolve anatomically. So neither MRA nor CTA nor even digital subtraction angiography can see these 100 micron diameter or smaller vessels. But with ASL, we are measuring their function because we're imaging the labeled blood in the microvasculature. And so one thought we had is that since Alzheimer's disease has regional patterns of hypoperfusion, but vascular disease is probably a more global effect, that perhaps vascular and neurodegenerative manifestations of CBF change can be differentiated. And so the image on the top is some recent work from my lab working with our ADRC that shows in blue the pattern of blood flow reduction associated with amyloid status, and red the pattern of blood flow reduction associated with vascular risk factor status. And you can see the red is more global, whereas the blue is the key areas of hippocampus, parietal cortex, and posterior cingulate and precuneus. So, and then on the graphs below, I also show region of interest analysis, and there's 4 groups, as you can see on the bottom: cognitively unimpaired amyloid negative, cognitively unimpaired amyloid positive, MCI amyloid positive, MCI, and dementia due to AT. And what you can see is in the canonical region that is most sensitive to CBF changes in AD, the PCP and precuneus, you can see a progressive decline in CBF across this AD continuum. But on the right, I'm showing the same type of region of interest analysis, but this is now from the normal appearing periventricular white matter, the deepest white matter. And that also shows significant differences. And the notion we're exploring, and that we hope to also explore in CLARiTI data, is the notion that these white matter changes might be indicative of microvascular contributions to vascular cognitive impairment, in addition to the gray matter contributions that we can see most clearly in PCC precuneus. So I think the next slide brings us to Terry's component of this. And I didn't introduce Terry, but Terry Ward is basically in charge, the person really in charge of advanced MRI in the CLARiTI administration. And so take it away, Terry.
Not even close, but I'm your friendly image analyst. But what I wanted to make sure that you guys were aware to send us an email at clarity@medicine.wis.edu if you're interested in these sequences. I think Konstantinos and Dylan and John did a great job of summing this up of what capabilities are here, and it's pretty exciting to see what we might be able to do with that data. Once again, just emphasizing that we are looking for multi-echo GRE for QSM, the motion corrected T1, and then a couple of different ASLs that are available as well. On the right, I wanted to point out that the top 3 Siemens sequences require an MTA. So if you're interested in using those sequences, please reach out to me sooner than later so that we can get things going with the legal teams if we need to. All the other ones do not require an MTA, so you should be able to move forward in a fairly straightforward manner. But please feel free to reach out to me if you have any questions. I'll route you to the right people if I don't have an answer. And then we'll make sure that you guys are up to speed and able to collect when you have your subawards. So I'm going to pass it to Heather O'Connell, talk a little bit about how this data moves through the pipeline. So take it away, Heather.
Yes, thanks, Terry. Yep, now that you've heard about the why and the what of advanced MRI, and Terry talked about how you get the protocols set up on your in your processes, I'm going to talk to you about the data management details about how advanced MRI will be processed in terms of submission, processing, and accessing the data. So first I'll talk you through the steps on this slide in a step-by-step fashion, and then I have some graphics that help depict that as well. So in terms of submission, currently all images will be submitted to LONI. Make sure that you select and identify that those images are going through the CLARiTI portal. So there is no different or special submission process for advanced MRI sequences, different from any other images that you're used to submitting for scan. In terms of processing, so the scan team will classify all the images submitted to LONI, and then they will QC and analyze any image that's deemed as scan compliant, so those T1 and flares. And then for the CLARiTI Advanced MRI sequences, those will be sent to the CLARiTI team for QC and analysis. In terms of accessing, you'll get those through the ADRC portal on a CLARiTI dashboard. And researchers everywhere will be accessing images either standalone or integrated with the other data modalities via the data front door, which enables those researchers to access all those modalities at no cost. So here's a graphic that outlines this process. So I'll be a little bit repetitive here, but the Alzheimer's disease research centers will submit the data to LONI. The scan team will assess that, and across the top there, the CLARiTI Advanced MRI will get sent immediately to the NACC data platform, where the CLARiTI team will process, QC, and analyze those within the NACC data platform, and the scan compliant sequences. The QC will be done at Mayo and analysis done at UC Davis according to the current processes. Those data will then, after that process, be submitted to the NACC data platform and merged together for sharing. Next slide, please. So more on accessing the data. As I mentioned, sites will be able to access CLARiTI data via the ADRC portal. This slide depicts the rendering of the interface at the ADRC portal. So you'll click on that CLARiTI card that will become available soon, and then you will be able to navigate to your ADRC's private CLARiTI dashboards. So this is where you'll be able to access, audit, and download your CLARiTI imaging data, along with all of your other CLARiTI data as well. But you can check QC, analysis, and the return of results status for submission. So for those of you, if you go to the next slide, please, you'll see more of that. So yes, this is where you'll be able to access those dashboards. And for those of you familiar with the scan dashboards, this should look pretty familiar to you. If you go to the next slide, once you click on the Advanced MRI dashboard, here is a sample of that where you'll be able to see key metrics. So in the upper left corner on the sample page, you can see total advanced MRI scans submitted, the QC status in the middle, series type counts on the right, and then below a listing of the details for each scan session. So these dashboards are currently under construction, but we wanted to give you a feel for what they might look like. On the next slide, this is for accessing for researchers everywhere that the CLARiTI Advanced MRI data will be available on NACC's data front door, which is the one-stop shop for ADRC participant data that's searchable, visualizable, and accessible. The key components that will be developed include the quick access files. So researchers can request data, sign a data use agreement, and access data collected from the ADRCs, including summary, QC status, analysis data, and eventually raw images. Real-time dashboard, a real-time public dashboard for CLARiTI will give researchers a sense of how many images and other data sets are available, so that can help them inform their quick access file requests. Also, an innovative cohort selection tool will be available that will enable researchers to build their own multimodal data sets. So that's what I had to share with you today in terms of submitting, processing, and accessing data. We look forward to rolling this out to you as sites become activated and participants enroll and scan. So it's a very exciting time. I think the key takeaways is to have your sites determine your site level scanning protocols that you're going to use and your plans for submitting data, which will likely be very similar to how you submit your scan images today. So with that, I'll pass it back to Beth, who I think will be available to answer questions along with the rest of the presenters.
Yeah, thanks, Heather, and thanks everyone from Advanced MRI for going through those slides with us. There's a couple, so yeah, if anybody wants to raise their hand and ask a question, you can do so. There's a couple of questions in the Q&A box that we can start off with. So the first question is, can sites substitute the motion corrected T1 for the standard scan T1? Or do they have to acquire both? So I think this is maybe more of a question for, so yeah, I think the answer is no to that. So the idea with CLARiTI was to, implement those 2 scan sequences across the board, and then to evaluate these additional sequences. I don't know if anybody wants to add.
So, Beth, I'll say it's no for 2 reasons. One is that, scan is quite particular about the exact parameters. And so that they will not accept anything other than basically the ADNI T1. But the other reason is that the research we're hoping to do with these data is to actually demonstrate the value of motion correction. And so, we would like to, for research purposes, to have both of those, at least initially. This may not be something that requires 5 years worth of data, but initially we would like to have both.
Thanks, John. All right, this next question I think is probably for a few of the advanced MRI folks. But beyond acquisition sequences, can you discuss some of the processing and analytic methods, approaches to harmonizing GRE, SWI, QSM, and ASL and multi-site studies across different vendors and scanner models?
Yeah, I mean, that is a good question, and it's I think probably more than we can really answer in the few minutes we have here. The original intent of the original approach we wanted to use for data analysis was to have a centralized cloud-based database of all the images in the Flywheel imaging informatics platform, and to use processing gears to quickly and hopefully almost effortlessly derive scalar values from the imaging data. Harmonizing those scalar values is a secondary step, and we do have, as part of our personnel on CLARiTI at Penn is Taki Shinohara, whose lab came up with combat and various derivatives of that. And so with sufficient data, we will be able to harmonize. I'm not sure there's a good way to harmonize the first few cases. And I think that really, so I think to me, the harmonization will be applied to derived scalar values rather than to the images themselves, but maybe others have a better answer for that. Apparently not.
All right, I think there's a question. Actually in the chat. There is a question about DWI and ASL on whether these would be able to detect early changes in neuronal connectivity and vascular dysfunction. So John, you went a little bit into the vascular question.
Yeah, so DWI is not currently part of the CLARiTI Advanced MRI protocol, but ASL is. And ASL, to a first approximation, gives a map of quantitative map of cerebral blood flow. ASL time series data can be used to study connectivity, but in this particular implementation of ASL, we are sacrificing our ability to detect fluctuations over time to get the best possible map of resting CBF, which is a state or trait-like property of the brain rather than a dynamic property. And we do believe, as I tried to explain in my complicated last slide that perhaps I shouldn't have even attempted, that there may be ways to differentiate kind of blood flow changes due to neurodegeneration from blood flow changes due to vascular dysfunction, because the latter might be expected to be more global and affect parts of the brain that aren't typically thought to be primarily affected by Alzheimer's disease and other neurodegenerative processes.
Thanks. And it sounds, I know there was also interested in DWI, but that's not included in this first round for CLARiTI. Okay, another question is, can you discriminate small vessel disease and blood-brain barrier damage dysfunction using advanced ASL methods?
Wow, okay. So again, small vessel disease is a disease affecting microvessels, and it's microvascular function that we're measuring with ASL. Blood-brain barrier dysfunction is much more challenging. There's evidence in the literature that certain ASL methods can measure not exactly blood-brain barrier dysfunction, but changes in water permeability at the blood-brain barrier with variations on ASL, but we are not attempting those. Those are scans that are very time-consuming, and one of our key goals in advanced MRI is to keep the total protocol down to a reasonable time to allow participating sites to do the scan required T1 and FLAIR, the entire advanced MRI protocol, and maybe a couple of sequences of their own. So I think the jury is still out on how effectively you can measure blood-brain barrier damage or dysfunction using ASL methods, and those are really we didn't feel those methods were ready or time efficient enough to deploy here.
All right, I think that might be it for questions. So yeah, I'd like to thank John and the team for an excellent set of presentations. Terry showed, an email address to reach out to for sites that are interested in, in launching advanced MRI these sequences at their site. Please, definitely reach out to Terry as soon as possible so you can start getting these MTAs in place. And then also want to plug the CLARiTI session one more time as well, which is going to be on Thursday at 4 p.m. And it's hybrid, so you can join remotely as well if you're not going to be there in person. And I think that's it for the webinar. So thanks again to John and the team, and Heather and Aaron for the study updates.
Thanks, everybody.
Great.
Good.